Hi everybody, it's David Williams. Today's topic is on capacitance and capacitors. And we're going to examine what capacitance is, as well as look at what a capacitor is. And as you might imagine, a capacitor is a device that has a certain amount of capacitance, designed to have a certain amount of capacitance. And we can see a few examples of some capacitors here in a little circuit. Now, before we get into an official definition of what capacitance is, let's say we have a little circuit right here with a voltage source, battery or something, call that Vs, and it's got two long wires connected to it. And now these two long wires, one's coming out the positive terminal, one's coming out the negative terminal, but these two long wires are not connected together. And so the instant that this battery is applied to these two long wires, this voltage source is applied to these two long wires, what is going to actually happen, even though we don't have a complete circuit, is electrons are going to want to flow out onto this wire and build up on this wire, and at the same time electrons are going to be pulled into the positive terminal, leaving a deficit of electrons on the positive wire, and the deficit of electrons is going to make that top side of the wire positively charged. And so this voltage source is going to be exerting a little bit of energy to push these electrons out and pull these electrons in. And so that energy that it's taken to push those electrons out and pull the other ones in is actually going to be stored in the form of these separated charges. And it's going to be stored in the form of the electric field that's created between the negative side and the positive side here. So it's a little tiny bit of work done by the voltage source, and that work is going to be stored between the two wires. Now let's take this a little bit further. Imagine that we've got two plates, two big plates here. One's connected to the positive side, and one's connected over here to the negative side. And let's imagine these plates are much bigger than I've actually drawn them. And so there's going to be room for a buildup of more charges on these plates. Lots more charges on these plates. I've just drawn three at the top and three at the bottom, but imagine if it was a really big plate, you could have lots of charges on both the top and the bottom. So when this voltage source is applied, lots of electrons are going to flow out on the wire, electrons are going to build up on the plate, and at the same time, electrons are going to, the free electrons that are on this metal wire and this metal plate here are going to flow off of the off of the plate, off the metal wire, and back to the voltage source. So you've got an even bigger buildup of charge between these two adjacent plates. And obviously at some point in time these plates are going to be saturated. You're not going to be able to build up any more electrons here, any more positive charges here, but we're going to be able to get a lot more electrons here than we did when we didn't have the plate. And so that voltage source is going to be doing a little bit of work to push those electrons onto the bottom plate and pull the electrons off the top plate. But it's a little bit more work than it did in the previous one, and that work that it's done is going to be stored in the electric field that's created between these two charged plates. And this little thought experiment demonstrates capacitance. Because capacitance, let me write out the definition for capacitance here. It's capacitance is the capability of adjacent conductors to hold some charges, a certain amount of charge, for a given amount of voltage between them. That's fundamentally what capacitance is, and we can sort of formalize this, I guess, in the form of an equation. Capacitance, C, is the capability to hold a certain amount of charge, Q, for a given voltage. So the first example where we did not have these plates, we pushed on a certain amount of charge, not very much charge, onto the two wires for a given voltage. And then we added, the second example, we added to the two parallel plates. We could push on more charge for the same amount of voltage. So in the second example, these two adjacent conductors had more capacitance in the second example than they did in the first example. So charge per given voltage, and if we want to look at this, what the SI units are, charge is going to be measured in coulombs. V obviously measured in voltage. So the SI unit for a capacitance is coulombs per volt, but we give it its own unit. We give it the unit farads, which just has the symbol F. And the farads are named after Michael Faraday, who he didn't invent or he didn't discover capacitance or capacitors, but he did come up with some of the first practical applications of capacitors. So one farad, 1F is the capability of adjacent conductors of storing 1 coulomb of charge when there's 1 volt potential difference between those two conductors. Now going back to this example here, if I was to increase the voltage here, I'm increasing the push, so I'm able to push more electrons onto the bottom plate and pull more electrons off the top plate. And I'm going to I never mentioned it, but we're going to have a balance. We're going to push the same number of electrons onto the bottom as we're going to pull off the top. So with higher voltage, we're going to be able to push more electrons onto the bottom and pull more off the top than we would with a lower voltage. And similarly, if I increase the capacitance of this overall system for the same voltage, I'm going to also be able to push on more electrons. And we saw that example with the comparison between the two wires and then comparison of the two wires to the two parallel plates. So there's actually 3 ways that I could increase the capacitance in this system here. So increase the capacitance of this parallel plate combination here. The first thing I can do to increase capacitance, so I want to increase the capacitance. So the first thing I can do, number 1, I can increase the area that's overlapping between the two adjacent conductors. So I make bigger plates up here. I'm going to be able to push more charges onto the plate for the same amount of voltage. So it's pretty straightforward. An increase in area is going to increase the capacitance. The second thing I can do is I can decrease the distance between the plates. Now this one's maybe a little bit more subtle, and the reason that if we decrease the distance between the plates, let's look at a cross-sectional area, or a cross-section view of these two parallel plates. So our top plate, we've got some positive charge, and then bottom plate we've got some negative charge. So if I decrease the distance between those two plates, what I'm doing is I'm increasing the capability of these positive charges to try to pull negative charges towards it. They're not going to be able to jump across because this is going to be a really good insulator. But remember, this is going to be, of course, connected to the voltage source. So the closer I am, the more pull this positive is going to have on the negative side. So I'm going to be able to pull more negative charges onto the plate. And the same can work the other way. As I'm moving it closer, these negatives, moving the negatives closer to this side, well, the electrons, any free electrons that are over here, are going to want to go away. So we let electrons, the negative charges, I want to go away from the negative charges on this side. Now the third way to increase the capacitance, now this is even more subtle, and it's probably a concept that you haven't seen before, and that's to change the substance, change the material that's between the plates. And what we're doing I say between the plates, but it really could be between any two adjacent conductors that have a voltage difference between them. So if I change material between the plates, what I want to do is change the dielectric to increase the dielectric constant, or in other words, the permittivity, and I'll come to a definition of what those are in a second. But the basic idea is between the plates, obviously, you need to have some kind of insulator, and that insulator is called the dielectric. And a dielectric, different dielectrics they're all insulators, but they've got the different properties of being able to polarize the molecules of the dielectric more or less. And to get an understanding of what polarization is, let's imagine that we've got an atom or a molecule here, and in the middle of the molecule, in the middle of the atom, I guess to be more precise here, we've got our nucleus, and we've got all these positive charges from the protons. I just drew 5 there, but that's just to represent some number. And then around, distributed evenly, not necessarily circularly, but evenly around the outside, we're going to have the electrons. Same number of electrons as you have at the outside as you have, same number of electrons as you have protons in the middle. Now, if we were to apply an electric field to this system, the nucleus will be unaffected. But what's going to happen to the electrons, let's say our field was oriented like this, so we have more negative on this side, more positive on this side. So our orientation of the electrons are going to be pulled towards the positive side. Now this is a very good insulator, so this atom's going to hold on to its electrons really strongly, but they will still be pulled towards the positive. And so what you end up with is that the net effect within the atom here, you're going to have a more negative on this side and more positive on this side. So you effectively create a dipole, and this is polarization. So we polarized this atom, or we polarize a molecule. So when you have polarized, when you have molecules in between the plates that can be polarized. Here's my 2 plates. One's the positive and one's the negative. Equal number of positive as negative, and I've got these molecules in here. And there's going to be obviously lots and lots of molecules. I'll just draw a few for representation. They're going to be polarized, so that this side will be more negative and this side will be more positive. And you can sort of think about the effect of this is that you've got the external, you've got the electric field created from the charges on the plates, polarizing the dipoles, polarizing the dielectric inside. But at the same time, because you're now more positive on this side from the dipoles of the dielectric, more positive on this side is going to want to pull more E negatives in, and the negative on this side is going to want to push more electrons out. So the more polarization you get with the dielectric, the more electrons you're going to be able to pull in on the bottom, and more that you're going to be able to push out on the top. And so the combination of these 3 effects on the overall capacitance allows us to calculate what the capacitance is for any two adjacent conductors. So the capacitance depends on the cross-sectional area overlap between the conductors, depends on the distance between the conductors, and it depends on a measure of the permittivity, or the capability of creating these dipoles in the material that's in between the 2 parallel plates. Just to give you an idea of this epsilon number, this permittivity number. So things like, I'll give you a few examples: vacuum and air, and something called FR4, which is a common dielectric that's used in printed circuit boards. It's basically the stuff that printed circuit boards, a common material that printed circuit boards are made out of. It's essentially just a glass reinforced epoxy that circuits traces are built upon, and then something that's got a very high capability of being polarized is barium titanate, and this is used in something called supercapacitors, and we'll talk about supercapacitors in a later video. And so the permittivity for these things, for a vacuum, 8.85 times 10 to the minus 12 farads per meter. 854. Let's go to 4 sig figs there. Air is a little bit better dielectric than a vacuum. 8.8898 times 10 to the minus 12 farads per meter. FR4 is a few times better. It's 4.24 times 10 to the minus 10 to the minus 11 farads per meter. And barium titanate is 1.06 times 10 to the minus 8 farads per meter. So like 1,000 times higher permittivity than a vacuum. And oftentimes things are measured in relationship to air, and we call this epsilon R, or just the relative permittivity compared to air, compared to a vacuum. So compared to a vacuum, the relative permittivity of a vacuum is just 1. Compared to a vacuum, the relative permittivity of air is 1.005, so it's 1.005 times bigger. FR4 is 4.8 times more, 4.8 times higher permittivity than a vacuum, and barium titanate is 1,200 times higher permittivity than a vacuum. So we've looked at the ideas of what capacitance is, as well as how much capacitance certain things can have based on their geometry. Here's a quick look at a picture from Wikipedia of some different capacitors. We've got ceramic capacitors, we've got electrolytic capacitors, we've got some disc capacitors, ceramic disc capacitors. So see, if you look at a circuit and you see things that are shaped like these ones, then you should be able to hopefully recognize them as capacitors. And I will be talking more about some of the applications and why you'd want to use a capacitor. And we'll also be looking at how capacitors behave in a circuit in some later videos. But I just want you to recognize some capacitors now, and just understand that they're often used in filtering signals, as well as in storing energy. Two sort of broad classes where capacitors could be used. And I wanted you to get a picture of what capacitors would be, so that when we're going to look at capacitors in circuits when they're connected either in series or in parallel. So if we've got capacitors in series, we have them connected like this, where this symbol here, or if we just draw the symbol like this, would be the symbol of a capacitor, the two parallel plates representing the capacitor. Of course, you could draw it in this orientation as well. And we could also have capacitors in parallel as well. And number 3. So if we've got C1, C2, and C3 over here, we don't know what the capacitance is, but just designate them as C1, C2, and C3. And we want to figure out what is the total capacitance here, and what is the total capacitance over here. Well, easy enough to figure out. What we need to recognize is that each one of these capacitors is going to have some amount of voltage across it, and the total voltage across all 3 capacitors is going to be equal to V1 plus V2 plus V3. And the other thing that may not be so obvious is that the amount of charge that builds up on this capacitor, and this capacitor is going to be the same. So we had the voltage source applied. We had electrons come in on this side. It's going to push out the same number of electrons on this side. The only place for them to go is to build up on here. So the same number of electrons will be here as over here. It's going to push out the same number of electrons on this side to build up over here and push out the same number of electrons on that side. So the total charge between this point and this point is going to be equal to the charge built up on 1, which will be equal to the charge on 2, which will be equal to the charge on 3. So from the definition, the total capacitance across this whole thing is going to be equal to however much charge we've been able to build up on it for the given amount of voltage that's across it. Well, we know that the total voltage is equal to V1 plus V2 plus V3. And now we'll just do a little bit of trickiness in algebra. We're going to invert both sides. So 1 over CT is equal to V1 plus V2 plus V3 over QT. or we'll just call it Q because it's the same Q on every one of them. So 1 over the total capacitance is equal to V1 over Q plus V2 over Q plus V3 over Q. And if you'll remember, capacitance is equal to Q over V. Well, here we have V over Q. So our total capacitance then is going to be equal to 1 over the capacitance of 1 plus 1 over the capacitance of 2 plus 1 over the capacitance of 3. So when we have capacitors in series, the inverse of the total capacitance is equal to the sum of the inverses of the individual capacitances that are in series. So opposite of resistors, actually. And now if we look at capacitors in parallel, we've got a total capacitance across these three in parallel. And what you should recognize is that when you have components in parallel, they're all going to have the same amount of voltage across them. So total voltage will be equal to the voltage across capacitor 1, capacitor 2, and capacitor 3. Now the total charge that's on this side, that's built up across these capacitors, is going to be equal to the charges built up on each one of the individual capacitors. And how much charge builds up depends on the value of each capacitor. But the sum of the three is going to add up to the total charge that's built up. Right? Charges come, electrons come in on this side. Some build up here, some build up on this plate, some build up on this plate, and push out equal amounts on the other side. So going back to the definition of what capacitance is, the total capacitance is going to be equal to the total charge divided by the voltage across the total system. And the total charge is equal to Q1 plus Q2 plus Q3. And then that's all divided by the total voltage, and the total voltage is going to be the same on V1, V2, and V3. So we can split that up, Q1 over V. So the total capacitance is equal to Q1 over V plus Q2 over V plus Q3 over V. And going back to what the definition of what capacitance is, charge for a given voltage. So Q1 over V, or V1, is equal to C1. Q2 over V is C2, and Q3 over V is C3. So the total capacitance is equal to C1 plus C2 plus C3. Now this is, again, opposite of the way that resistors in parallel work. Finally, one last point of capacitors in circuits. We'll do more details of capacitors in circuits in later videos. But like I said before, one of the purposes of a capacitor is to store energy. And energy for different things. Maybe I mean, even a filter is sort of a way of storing energy. But it could be, as complex or as a large amount of energy as replacing a battery, or it could be as simple as just storing enough energy in case there's a sag of the voltage supplied from a voltage source. And the amount of energy that is stored in a capacitor is equal to 1/2 times the capacitance of the capacitor times the voltage squared. And this is fairly simple to derive. It does involve some calculus, and it does involve some understanding of the relationship between voltage and current in a capacitor. But we're going to get to those concepts at least the concept of the relationship between voltage and current in a capacitor in a later video. So anyway, hope you learned something about capacitors, and I will see you soon.